Hello everybody, in this video I will show you how to deal and solve problems with junction diode. So what is a junction diode? Junction diode is a nonlinear element. What does it mean? So let's look at resistor before. A resistor in which the Ohm's law works, okay? If we plot the current as a function of the applied voltage, in which we have here the convention of the sign of the current and the voltage difference we apply to the resistor, if we plot the Ohm's law in a Cartesian plot with the current on the vertical axis and the voltage on the horizontal axis, we will have basically a line with a slope which is 1 over r. Okay, so this is the reason why we call this a linear element, because a line in the plane EV describes its behavior. The diode is a non-linear element. The reason why is because we have a semiconductor junction, PN junction, and so the microscopic behavior and elements and physics of the diode, you can find a lot of knowledge and very beautiful video on YouTube. Now, or in books also. Now I will just focus on the macroscopic behavior of this thing. So we say that this is a non-linear element because actually instead of a line, we have this curve, which is actually an exponential. The Shockley diode equation is this one that you can find also many books and elements in which we have a lot of parameters that basically add confusion, not add confusion, but give a very specific vision of the thing. But here I want just to resume this behavior, just saying that basically this curve is something like E current proportional to the exponential of the applied voltage, which have also this here in a more complex and specific way, but basically this is what we have in this plane. So this is the real curve of the diode. If we measure the current flowing into the diode in this direction with an applied voltage with this polarity, we will have this exponential curve. However, in an ideal diode, we want to deal with some more simple element. And actually, we approximate something nonlinear into a two-linear segment function. So basically, we approximate this real curve into this. Let me draw this. We'll try to do this properly. So a vertical line here and an horizontal line here. Okay, so this L stuff. The real thing is this exponential stuff, but we will see that this approximation is very okay for understanding the behavior of the diode and also for working with it in problems as a first ideal approximation. So with this curve, we can define a parameter which we call usually VF, forward voltage, which define the two regions of operation of the diode. Below the forward voltage, we have the diode which is off, because actually the current is zero in any of these points. Okay, so we say that the voltage is off. Above VF, we have that the diode is in on state. So we have current, some value of current here, which can be on this line, okay, and a fixed voltage VF. Okay, so for the moment, just recall again that the real curve is the black one, but we don't care about the real curve, exponential curve, and we approximate this behavior of the diode with these two segment function. Okay, so we have two linear segments which approximate a nonlinear function. So now let's state something more specific and convert this graph into equivalent circuit. So if we have that V applied to the diode is less than some VF, this VF, which is usually VF equal to 0.7 volt, Okay, if this is the applied voltage to the diode is less than this value, we have the off state, so that I is equal to 0 and V can be any value. 0 and V can be any value below. So E is 0 and V can be any value here on this line. Okay? If the applied voltage to the diode is greater than VF, the diode is on, V is equal to VF, and I, the current, can be anything. What does it mean? That we are basically on this line here. The V is fixed to this value, but the current can be any of these value here on the line. Okay, so the main problem with diodes, in my experience, is this thing, this at first sight contradiction, which we don't know, we don't understand if the V of the diode is more than VF or is VF. So this is the big deal, okay? So let's see now this with an example. So yes, the contradiction is given by the thing that V, the thing V here in this side of the equation is the voltage seen by the diode. What does it mean, the voltage seen by the diode? So let's look at some real circuit, something like this, in which we have a voltage source, a resistor, and a diode like this. We also have the ground here. So we have here a simple mesh. We call this R. We call this, let's say, VA. And we want to know when the diode is on, and basically we want to know the current and voltage of the diode depending on this applied voltage. So what we have to do is to remove from this circuit the diode. First of all, I'm not turning off the diode, I'm removing the diode, okay? And just move this away. And here I place my voltage, I will call this VD, which is the voltage seen by a diode given the external circuit, which is in this case this thing here. So let's see this mesh and see how much is VD. This mesh is very simple because we have no current flowing into R, because basically we have an open circuit here. Okay, so no current can flow in this mesh. So there is no voltage drop into R, and we can write down, I know it's very simple, but we can write down the mesh equation. So you start counting from here, one jump of voltage here, 0 jump, then another jump, and then we are back. So as I explained it in the previous video, basically you can say VA with a positive sign because we first find the minus here. VA minus VD is equal 0. This is by solving this mesh, just the mesh. It's an open circuit. We don't care if there is a diode here or anything else. We just remove the diode here. We see this voltage drop between this point. And for this specific circuit, we have this equation here. So basically here in this circuit, we have that VD is equal to VA. Okay, so now we can say that if VD is more than VF, which in this case is the same that VA is more than VF, our diode is on. And the VD is a fixed voltage VF. So in this case, in which is on, we can change the diode for a fixed battery. Okay, this thing here, we delete. We can leave this here, but I mean, we just have to remember that now it's a fixed value. So now this thing is VF. Okay, so let's see what happened to this circuit in this case. Let's consider a real, some real values. For example, VF is equal to 0.7 volt, which is the typical value of a forward voltage for a junction diode. And our VA is, let's say, 8 volt, for example. So we are satisfying this condition, okay? So this voltage is 8 volt. And in the previous case in which we removed the diode, the voltage seen by the diode is 8 volt. Let's come back one moment to the picture of before. I mean, the applied voltage is, let's think that VF is 0.7, okay, and the applied voltage is 8, so something, for example, here or here, whatever, I mean, written the value. As you can see, the curve of the diode is fixed to VF, so the voltage in the diode cannot be 8 volt. So what happened? Basically, now we solve this mesh, which is different from the previous one in which we have removed the diode, and see what we have. So now the mesh is closed. So we will have some current flowing. And actually we know that the current flow when the diode is on in the direction of this arrow. Okay, so this reason for this symbol. When this diode is on, the current flow in this direction. So in this mesh, we have a current here. We can call it IA, for example. Why not? Any name is good. And this current here and this resistor will cause a voltage drop here. Okay? We call this also, we can call this VR, for example, or V0. I mean, the name are very not relevant. So let's do this mesh again. We have a voltage jump here, a voltage jump here, a voltage jump here, and then we close the mesh. So now in this case, this is something like VA minus VO minus VF equal 0. We can say also that VA minus IA times R minus FVF is equal 0. So let's find out how much is this voltage drop. First of all, IA times R equal to VA minus VF equal to 7.3 volt, because we have 8 volt minus 0.7. So basically we have here a voltage drop of 7.3, here we have a voltage drop of 8, and here we have 0.07. Okay, so the excess voltage falls into this resistor here and set the current value which flow in the mesh, which means also through the diode. Okay, so for example, if we take a R of 1 kilo ohm, in this case we have that IA is equal to 7.3 milliampere. What does it mean? That we have on this curve now the operating point of the diode is something here on this line with coordinates 7.3 milliampere and 0.7 volt. Okay. Now, if we want to see the case of the diode off, let's consider another value of VA. So we can redo this. Yes, it's okay. We do it again. So at the beginning, we had our circuit with VA here, R, and the diode, like this, and the ground. So again, if we want to see what happened to the diode, we have to delete this circuit in this point and remove the diode from the circuit. So we take this away from our circuit, and again we name this voltage drop with the polarity according to the diode VD. We see the mesh. Again, we have that VD is equal to VA because there is no current flowing in this mesh due to this open circuit here. Again, we don't care what is here. We just remove the component, in this case a diode. So that voltage seen at this point is VA. In this case, let's consider VA equal to, let's say, minus 1 volt, for example. Or it can be also 0.5. Okay, let's do 0.5. 0.5 volt, for example. This is less than VF, so our diode is off. Is off means that instead of a battery, we can put an open circuit. Why an open circuit? This open circuit now symbolizes that the current flowing into the diode is equal to 0. So this open circuit now represents this line here. This line here. Before, this line here is represented by an open circuit instead of the diode. Previously, when we were in this line here, we represented this fixed value VF by substituting the diode with the battery with value VF. Okay? So we will see this again later. For the moment, let's continue with the circuit. So, in this case, everything is much simple. In this mesh, we have that VD is actually equal to VA. That is, VD is equal to 0.5 volt here. And the current is 0. So now, this is our operating point. On the diode curve, this means that we are in some place here. Let's see where we are. Some place here. 0 current and 0.5 volt. Okay? So we can resume all these things that we've seen up to now with two regimes. If the voltage seen by the diode is less than VF, the diode is basically an open circuit. And if the voltage seen by the diode is more than VF, the diode is a battery with this polarity with value VF. This battery is symbolic. This is not a power source, just represent a fixed value. Okay, so, and what we have to keep in mind that this VD here is what we have when we remove the diode from the circuit. When we remove, in this case, the circuit was this one, with the voltage source and the resistor, we break the circuit, we remove this, and the VD is this voltage here, seen in the place of the diode, taken with the polarity of the diode. Okay, if the diode was in this circuit upside down, we should put VD with this polarity. So, in this first video, I made this simple example as a first introduction to the diode. In the next video, I will give other example in order to better understand this concept. I hope this video will be helpful to you and it was clear. Please comment any suggestion in the comment section. Thank you for watching.